This video describes how to go over the input file of the NGA code. So usually the input file of the NGA code has the name input, but depending on um, your your preference, you can name it differently. You just need to specify a different file name. So here, as you can see, I create a directory in the Scratch folder of the Soul cluster. So you always want to run your simulation in the Scratch folder. You don't want to run your simulation in your home directory, which is, say, home. That's my ASU Ride ID. So, so this is my home directory. You don't want to run any of the simulation in this at this home directory. You want to move everything to the Scratch folder. Otherwise, you'll be able to receive an email from the ASU Research Computing in case that your the files, the number of the files or size of the files you're generating from your simulation is getting too big, and you can easily hit the space limit given to individual account. So anyway, so this is my Scratch folder, and I created the homogeneous isotropic turbulence folder in which I'm going to run an NGA simulation. The first thing you need to do to run the NGA simulation is to create an input file. So it's better to follow the convention, even though you actually don't have to name it as an input, but I usually prefer using this input, INPUT. So let's see what I have in this input file. It's just a text file. You can just use a VI editor or the Emacs editor and whichever text editor you want. But I'm recommending to use the text the traditional the text based terminal, not the web based the interactive session. So use this terminal. So there is a built-in terminal in Mac OS X. So my suggestion is to use this terminal. So VIN input, and let's see what's inside. So I'm going to explain. I'm going to go one input item by item. So in the first block of the input file, we have initialized parameters. So there is a code called initflow, init underscore flow. So that's going to be the code you need to execute. Then this part of the input file is used by the initflow. Okay, so this block contains everything about the simulation initialization. So the first one is called the simulation. So basically, it tells you what the simulation is, what is the simulation, what the simulation is the simulating, the code is simulating. So if you have, so there are some input deck items here. So whenever you run into something you don't know, you want to go into the source code instead of asking the advisor. I mean, of course you can ask, but you actually need to put some effort, then ask if you cannot find it. So, and then my suggestion, this is the text editor I'm using. So it's called the BB Edit. I'm not really asking you to use this one, but if you don't have any preferred text editor, this is a great choice. It has many options. So what this code can do is that you want to keep the local copy of the NGA in your so this is BB Edit. So if I open up, then there is this blank file showing up. So if you in your Mac, if you press Shift Command and F, Shift Command and F, then it's going to open up this multi-file search. And what I did was that let's find this the input deck item is telling you. So, and what other options I have. So I'm going to find out the simulation. Note that there's a capital letter. So this is a case sensitive. So it distinguishes lowercase and the capital the letter, and the entire word has to match. So I enable these two things. And where do I find this expression? Press other, then So this is my NGA source code. You can see that this is NGA source code. And in this source code, I'll be finding this expression simulation starting with capital S, find all. And I want to make it smaller. So you can see that there are multiple places in the code where this thing shows up, okay? So maybe this one, init flow, okay? So by the way, this is the, sorry, I just make or the character size pretty large so that I can show this everything more clearly. So whenever you see, if there is any subroutine of the Fortran starting with parser, that means that it's reading input deck from the input file I input. Okay, so so this simulation will be stored in this variable starting with lowercase s simulation. Okay, so then and if you go down and it doesn't necessarily it's not necessary below this subroutine parser, but you can see that this variable, depending on the what you have in this variable simulation, then the code branches into the different cases so that the simulation can be initialized differently. Say, if you, for example, if the simulation variable contains the resolved particles, it executes the different subroutines. So in our case, which is isotropic turbulence, let's copy and paste. Command C, copy. Then I want to go back to the init flow and I want to search the Command F. And I want to search this isotropic turbulence in this particular file, initflow.f90. Then if I specify isotropic turbulence for this variable simulation, then these in my version, my branch of the NGA, this in this case, for initialization, these 6 subroutines are executed. Okay, then this is how you follow the code. Your input file and the input file items, in particular the one on the left-hand side of this column, will describe what this expression is for. Then you need to check the code yourself so that you can understand. So of course, if you just see this line number 4, there's no way that what this variable simulation does. I mean, then a lazy student will just ask the advisor, but be proactive and you want to find the source code yourself. And there is something called the data type. So NGA can run some combustion simulation. So if it's a code, you want to use code unless you are interested in the simulating chemically reacting flow. In other words, turbo combustion. And here is a domain size. So in this particular case of the isotropic turbulence, the domain size is 2 pi. So if I bring this calculator, if I have 2 times pi, that's going to be 6.28 something. So domain size is 2 pi, and it's a domain size is 2 pi in every 3 direction. In this case of the isotropic turbulence, it is assuming that the domain size is the same in all 3 directions. Therefore, the domain is actually a cube, having the same length, side length of the 2 pi. And the number of the grid points along these individual directions is 32. This is 32 cube grid points. And for this particular case of isotropic turbulence, we are assuming that the domain is periodic in all 3 directions. And there is a velocity spectrum. So there is something called the spectrum form. Again, if you're not sure about what this variable is, you want to go back to the source code. And let's close this one. And here, paste the spectrum form, then case sensitive, entire word, then find all. And it's too big. So do I have that expression in the source code? Yes, we do. So in the DNS box, okay? So if I go in, then the spectrum form, any expression given for this spectrum form here, in this particular case of my input file, this capital PP, this is for Parser-Poquet spectrum. If you're not sure about this, then either check the Stephen Pope's Turbulent Flows book or Davidson's a turbulence book. Okay, copy and paste the capital PP, and so this PP is store this variable all lowercase spectrum. So let's try to find out where this capital PP shows up in this file, DNS underscore box.f19. So PP shows up here. This is sort of the expression for the Paso-Porque spectrum. You have another option, I think the von Karman and something, I forgot what was the P. But anyway, so there are several options for the initial velocity spectrum. So it's about how you initialize the isotropic turbulence so that it can be as isotropic as possible and as homogeneous as possible. I think the isotropy is kind of enforced and homogeneity is also enforced, but it's the form of the spectrum that you are initializing. So there are many other options. So fluctuation, you want to go into the source code and find it, okay? So then energetic scale, these three are all specific to the initial velocity spectrum. And whenever you see anything related to particle, you can skip. That's why it's commented out. Of course, if you're a Professor Kasbawi student, you don't want to ignore anything about particle, but I'm using NGA mainly, my research group uses NGA mainly for the turbulence simulation. So everything about the particles are pretty much the commented out. And here is the initial file. Basically this data.init contains all the initial condition. You need to have this file so that you can run the simulation. Again, part, basically particle. I don't need a particle information, so that's why it's commented out. Any optional data, so this all depends on your simulation case. For my simulation, I remove the comment symbol, but in your case, you may need it. You may not need it. And the init config file, so this is basically all the grid information, any kind of the geometry, and all the simulation, which is not containing any flow information, which is contained in the data.init. So these are some of the initialization parameters you need to get familiar with. You need to understand everything. If you don't need to understand some of these items, then I'll explain that. I'll mention that explicitly. So the second block of the input file contains all the running parameters. So these parameters are necessary so that you can run your simulation. So the first block is about initialization. Second block is about this time advancement of your simulation. And the third block is basically particle. So particle parameters, that's why they are all commented out. But again, if you're doing any particle laden turbulence simulation, like the Professor Kasbau is doing, then you don't want to ignore this, okay? So then let's go back to the second block because I'm not going to talk about the second block, a third block. So what running parameters do we have? So first, this is a config. So of course, you have this config. Basically, you specify this name one more time. So this is the initial config file generated by running the init flow code. Then you want to specify the same name here so that the NGA code, its executable file, can read this grid file. And you also want to specify the data.init here, the same name. But if you want to rerun your simulation, basically after you run the simulation, you want to continue running simulation, then you want to definitely change this name, okay? Then what is the name of the file generated? You don't want to change this. You want to keep this as a data, okay? Don't change this. And option of data file to read. So you can just skip it. You just match the optional data file name, and you don't want to change this OPT data as well, optional data. So data frequency here, again, if you're not sure of some of the input tag item, just copy and paste into your text editor and find it in your local repository. So then it's going to show you, usually there are multiple places, but if you're lucky, there's only one place. So whatever number you have for this data frequency. In this particular case, it's a 0.1. It's shown here. It's going to be stored this variable called the data underscore freq. So let's see what we have. Command F, and let's find this expression. So basically, if your current the simulation time, if you divide this by data freq, then if you take this integer form, basically round off, then basically this tells you how frequently your data should be written in terms of the time unit. Okay, so in this particular case, then we are writing this source the data file, this data, every 0.1 time unit. It's not second. Do not use a second, or do not use any of the dimension when you're giving this variable. So everything you should assume that this is dimensionless. Okay. So not sure about what data override is. Maybe we are overriding the data if we have a same. But again, just find it yourself. And this MPI IOFS, you probably don't want to change it. I actually forgot what this MPI IOFS is. It's definitely related to parallel file input and output, file reading and writing. But if you're not sure about something, it's the best thing to do is not to change it. So here, these are the parameters about the domain decomposition. So we have, as I said, for this isotropic turbulence, we have a cube. And this person who set up this the input file chose to have seven processors along the x direction, 4 processors along the y direction, 3 processors along the z direction. You can use a 1-1-1, you can use 1-2-1, and there's actually you need to actually do some test so that which choice of the number of the processors in all 3 directions gives the best performance, instead of just arbitrarily choosing. Okay, so but I'll probably describe in the different the video, or you can just ask me. And the third group of the items is called the chemistry, but this is not really as you can see, since this is a cold flow, therefore we don't have any combustion, therefore there is no chemistry model. You just want to choose the none. But we still use this value, density and viscosity, even if the case is cold, flow is cold. So in this case, density is assumed as 1. So again, the unit is not explicitly given, so you need to assume that all the variables are dimensionless. There is no meter, second, or kilogram. Do not use that. So then viscosity is probably the 0.05. I think this is because the density is 1, the kinematic viscosity is also 0.05. So it usually gives your Reynolds number based on the, you can estimate the Reynolds number based on this viscosity. And I don't think these 3 items are used. Otherwise, you definitely want to check where these variables are actually used. So then the next item is about how to force the isotropic turbulence. I'll probably skip this because this is too technical. So if you have a question, you can always ask me if your isotropic turbulence simulation has to be forced so that it can be sustained. So the next items are about the subgrid scale model, basically large eddy simulation. If you do the large eddy simulation, then set this variable to 0. Then you're running the direct numerical simulation. If you set this thing to be 1, you're running large eddy simulation. And there are multiple different averaging technique. And again, if you're not sure about what this variable is and you are doing LDS, then again, go to your text editor and find this expression, SGS averaging. And there's one place where this SGS averaging shows up. So this value, in this case, it's a constant, is contained in this AVG underscore model. What do I have in this variable? So this variable can have multiple different expressions. The first one is Germano. It's a Germano model. I don't know what ad hoc models are. Let's ignore this. And Lagrangian model by the Menable and colleagues. And constant is doing nothing. It's actually the classic Smagorinsky model, but I'll skip this expression. Okay. So then, so some of the optional, there are some optional things like this forcing and logic dissimulation. But these things, time advancement is quite important. So time step size, it's basically delta t for your time advancement. In this particular case, it's fixed as a 0.0001, but there are two the criterion. You can either specify time step size or you can specify the CFL number. But what code does is that it chooses a smaller time step size. So if you specify CFL number from your CFD class, then you can compute the time step size from this CFL number. Then what code does is it compares the computational time step size determined from this CFL condition, and it's going to compare with the time step size you specify here. The code will use a smaller one, okay? So do not complain if you set the CFL number too small, then sometimes you see the time step size different from this number you specified here, but do not complain, okay? Because it's you who set up the CFL number very small. And there is something called the sub-iteration. Let's keep this number as 2. If you're curious, look at the Desjardins JCP paper, and I think it's 2000 something, 2004 or 5. And because I have for the isotropic turbulence case, it's best to use the implicit direction XYZ because every 3 direction is periodic. So I'm not 100% familiar with all the numerics, but the bottom line is that if you have a periodic direction, you want to use the implicit formulation along that direction. So in our case, in this case, the isotropic turbulence has a 3 periodic direction. That's why XYZ is chosen. If only the Z direction is a periodic, then you want to specify Z here. And the end of simulation, when your simulation basically stops. So in this particular the input items, if you reach the number of the time step of the 20,000, or if your simulation reaches the time unit of 2, basically you do the time advancement from time 0, and you determine your time step size from either from time step size or either from the CFL number, then you run your simulation up to time equal to 2, then you stop. And or if your simulation has been running, say, greater than 10,000 hours, then your simulation stops. If any of these 3 is satisfied, the code will stop, whichever comes first, okay? And schemes, so I cannot go into too much into the details of the NGA, but basically for convection term, it is using second order discretization. For viscous term, it uses second order discretization. I believe NGA has different options, but for now, I'll be using second order accuracy. And for isotropic turbulence, we're not simulating any additional scalar. So, but if you're transporting any scalar, then this third order Wiener scheme is used. And pressure solver is always a pain for incompressible flow simulation. So these set of the variables are describing how the pressure solver is described. So here, I think it's using precondition conjugate gradient, and there is some specific preconditioner and convergence criterion of the pressure. If the error is less than 10 to the minus 8, then you assume that the pressure solver has converged. So maximum iteration is limited to 100. So you could specify different options, but you definitely want to talk to Professor Kasbawi if your pressure solver is not converging, even if you make this pressure convergence large, or even if you make this pressure iteration number very high, say greater than 1,000. So the next one is about the output, but in my case, I commented out, but if there is any preferred file format in which you're writing in which you'd like to write a data file, 3D data file, you can just specify here. So then again, output type, let's go back to the BB edit, then copy and paste, and let's make it small. So these variables are used in the dump underscore data. So then parser read, and in my case, it's a plus 3D, 3D. So what do I have here? This is contained in this variable output underscore type, and depending on the output underscore type, you have multiple options. You can use either inside, this is the name of the post-processing code. You can choose the plus 3D, which I have here. And I remember Dr. Kaspar's group is using Visit. I'm not using that, but H5 it can be I think so, this is a HDF5 format, okay? So I think I went over every item. So again, do your own work, okay, before asking an advisor. Just search for the source code and make some effort instead of just directly going to the advisor and complain and ask, okay? So this is what everything I have today. Then I'll see you in the next video.